Hello, and welcome to Video AAPT, a virtual workshop series run in partnership with Physics Today. I'm Mike Hall, Director of Membership for the American Association of Physics Teachers. Before we begin, let's go over a few housekeeping items. At the bottom of your screen, there's a floating menu bar with shortcuts to the tools for engaging with this workshop. These are resizable and movable, so you're welcome to move them around to get the most out of your monitor space. At the far left of the bottom toolbar is the media player control for viewing the speaker. Also, you can expand the slide frame by clicking on the arrows in the top right corner. There's a resources tab, and we request that you download the prediction sheet, which will be used for the first presentation tonight. There are two different ways for you to interact in these workshops. There's the chat and the Q&A, which is labeled Ask Questions. If you haven't already done so, please feel free to introduce yourself in the chat. Tell us who you are, where you're located, what you teach. Although we will be monitoring and participating as much as we can, you can expect that the chat will largely be a conversation among the attendees. However, if you have a question or comment that you would like to get in front of the presenters, please submit that through the Ask Questions frame. I will be monitoring the incoming questions and interjecting from time to time. Please help us make this virtual workshop interactive by submitting questions throughout the event. If you are experiencing any difficulties, please feel free to enter any questions through the Ask Questions frame. A recording of this event will be available after the event concludes and can be accessed using the same audience link sent to you earlier. If you enjoyed the workshop, you could also share the link with colleagues so that they can view it on demand. Our first presenters of the evening tonight are David Sokoloff of University of Oregon and Ron Thornton of Tufts University. And at this time, it is my pleasure to turn it over to David.
Thank you, Mike, and I'm very pleased to be here. I'm going to share my screen now, and so we can get started. And I'm going to get my PowerPoint going. So this part of the session will be on interactive lecture demonstrations, both in class and virtual ones. And as Mike said, I will be presenting, and also Ron Thornton will be presenting a little bit later. I want to mention that we are members of the activity-based physics group, and the principal members have been me, Ron, and Priscilla Laws, and this group was the winner of the 2010 American Physical Society Excellence in Physics Education Award. And just one very sad note, and that is that Priscilla passed away in December, and we're very, very sad that she is no longer with us. So the problem that we're addressing is that physics education research has told us very clearly over the last 20 to 30 years that students' experience in an introductory physics course seems something like this. Bart's experience here: I will not learn concepts in physics class. So the majority of intro physics students do not change their often incorrect conceptual views of physics if taught using traditional methods. Or another way of looking at this, most students spend the majority of their time in a traditional lecture, and it's often a large one. And I've always loved this Gary Larson cartoon with a slightly changed caption on it. Or we might think of Sheldon and his perfectly designed lectures, logical and sublimely entertaining, and yet we know from physics education research that students do not learn physics concepts from them. And by the way, you might be entertained by the fact that Sheldon is reading the American Journal of Physics, which is an education journal, as you know. So the question for us is, can an active learning environment be created in a large or small lecture? And our answer is yes, through the use of interactive lecture demonstrations. And so the best way to tell you what interactive lecture demonstrations is to do one with you. And within the limits of the platform that we're working on, we will now do an example of interactive lecture demonstrations. So either you have downloaded the prediction sheet, as Mike asked you to do, or you can download it now at the link in the resources, or you can just view it in my PowerPoint. Any one of these will work just as well right now. And let me make a note up front that predictions are never graded, because student predictions are what the students believe in the moment based on everything that they have studied up until that moment. And if you grade predictions, then students will be put in a position where they are trying to predict what you want them to think, not what they actually think. So we're going to do this demonstration. It's the first one on your prediction sheet, and I've reproduced that section of the prediction sheet here in this slide. And the situation is that there is a motion sensor to the left. There is a low friction cart. There's a fan on that low friction cart. It's blowing towards the right, and the positive direction is towards the right. And I'm going to give that cart a push to the right. It's going to move to the right, and of course, eventually it's going to reverse itself and come back again, and I'll show you what that looks like, and hopefully you can view this video as I play it. So here we go. I'm going to play it one more time for you. And I hope you were able to see a smooth motion of the cart. And what we ask you to do now is either, preferably by writing it down, and it could be just a prediction of what the velocity versus time for the cart will be, and what the acceleration versus time for the cart will be from the moment it left my hand until the moment just before I stopped it. So please go ahead. I'm going to give you 1 minute to do that. Think about it and make a prediction. Okay, 20 more seconds. Okay, so we're going to move on. So I've already said that. Now, if this were a real lecture class, then in the class, we would have the students discuss their predictions with the group of students that's closest to them. 3 or 4 students is fine. 2 can work as well. And then after discussing for a few minutes, we would ask for volunteers from the class to describe what their group agreed on to the entire class. So we can't do those steps on here, unfortunately, but we would have done it. And the next step in the ILD procedure would be to do the demonstration again, but this time display the data that are collected by the motion detector. So here we go. Okay, I'm going to go back. I'm going to do it again for you. So now the data have been collected, and the next step would be to ask for volunteers to describe what they observed and to explain it. And I'm going to now turn this over to Ron to describe the 8 steps of the ILD procedure. We've talked about 4 of them so far, but go ahead, Ron.
Okay. So the first step, describe the demonstration and do it for the class without displaying the results. Second step is ask students to record individual predictions on the prediction sheet. Have the class engage in small group discussions. Elicit common student predictions from the whole class, which you'll know after doing it a few times. Ask each student to record final predictions on the prediction sheet, which will be collected, not graded, but collected. Carry out the demonstration and display the results. Ask a few students to describe the results, don't tell them, and discuss them in the context of the demonstration. Students may fill out the results sheet if they choose.
And the result sheet, by the way, is a sheet that's identical, looks identically to the prediction sheet, but it's a record for them to take home with them.
And if it's appropriate, discuss an analogous physical situations with different surface features. They look different, but they're really the same, or an application of the concept. And this procedure is followed for each of the short little lecture demonstrations. Usually within a class period, there's 7 or 8 of them. And this whole thing goes through for each one. We're going to show you, not actually do it, but another demonstration. What?
I'm sorry, if I could interrupt, we have a question. The question coming in is from Tommy. It's, if nobody wants to share their prediction, how do you encourage their participation?
It turns out in most classrooms, certainly after the first few times they've done it, people seem fairly anxious to share. One of the things is that we don't say what's your prediction, what did your group decide on? So there's little penalty for being wrong, so-called. And we just haven't had trouble with that happening.
Okay. So go ahead, Ron.
Okay. Well, we're going to show you just one more thing. We're not going to actually run it. But this is the ball toss. You can see David there about to toss a ball into the air. And then after he tosses it, the result is shown on the right here. And if you check the acceleration, which is the bottom graph there, the value is very close to 9.8. So,
but you can see that the shapes have the identical shape to the cart moving away and back. And so students have actually discovered that there must be a constant force, which of course is the gravitational force in the room.
Now, do students learn concepts from the force and motion ILDs? Yes, you can see examples of dramatic, robust learning gains using the mechanics ILDs on the force and motion conceptual evaluation in the physics teacher article that's linked in resources.
So please download that article when you get a chance to do it. Okay, so of course the other question we might ask is, do students learn from traditional demonstrations? Because I think most physics instructors love to do physics demonstrations. And the answer from physics education research is probably not. And there was a study done, actually several studies done, where students who were not asked to make a prediction before seeing a demonstration in class were not even able to describe the result of the experiment that was done in class correctly. So it seems like many of our most treasured lecture demonstrations are just too complex for much learning of concepts to result. So there's a book called Interactive Lecture Demonstrations. It contains materials for ILDs on 28 different topics, student prediction and results sheets, which can be copied for your students, instructor's guide for each set of ILDs, teacher preparation notes that you can take to class to remind you what to do, the 8-step process, suitable for framing, and this book is free from Wiley, or please don't tell Wiley this, but there's a link in resources and you can download the entire book electronically after this session is over, or now for that matter. Okay, Ron.
So what are the characteristics of the ILD learning environment that make it effective?
Oops.
Yeah. Making predictions requires students to consider their beliefs before making observations of the physical world. The differences between their predictions, defended in small groups, and the result causes the result of the experiments causes disequilibrium and creates a learning opportunity. Students' knowledge is constructed from observations of the physical world, not what a physics professor or teacher is telling them, and it builds their confidence as scientists. So if you want to incorporate ILDs into your course, you can use it for introduction, review, or clarification of concepts. You could also develop your own ILDs, but it's not easy to do, and the only way to do it effectively is to do an awful lot of research on how students respond to what you've got down. No special classroom design is needed for ILDs. The lecture format, or it doesn't have to be a special thing like workshop physics, so it works there also. And on course evaluations, students say that ILDs are the thing they like most about the course, and they often ask if they could have more of them.
Okay, so now, because this session is on virtual, the rest of our part will be on home-adapted ILDs, which are an adaptation of the ILD strategy for use by students at home. So I want to talk about the design features and considerations of them. So home-adapted ILDs are based on the in-class ones, which are in the book, of course. They also are for learning concepts. They're envisioned as just one of a number of possible at-home components of a course. So they could be used for homework or for pre-lectures or things like that. They envision students working alone online, although if you wanted to have them do things with breakout groups talking to each other, they could be adapted in that way. And they make use of available multimedia, which means videos, photos, graphs, interactive simulations, and Phizlets for experimental observations rather than seeing live experiments or live demonstrations. So what we want to do for the rest of this session is have you work with a couple of home-adapted ILDs. That's the best way for you to get the experience. And if you go to resources, there is a link. And if you click on the link, it will take you to this page. So I'd like you to do that right now. Find the link in resources for home-adapted ILDs. and click on it. I'm going to close this window because I want to go back to my PowerPoint, but you should be on the home ILD page. And what I'm going to ask you to do for about the next 5 minutes or so is to click on number 17, which is image formation with lenses. And you're going to, as I said, you'll have about 5 minutes to work on it. And the first step it will say is to download the prediction sheet and then follow the directions. So I'm going to turn you loose now for about 5 minutes, and then I'm going to come back and start up Rise and give you an opportunity to comment if you have some comments on this. So please go ahead right now. Okay, 1 more minute. 20 seconds. Okay, if you could please come back to the presentation window. And of course, you can work on these after this session as much as you want, and I'll say a little more about that. So as you may have seen, I don't know if you got far enough, you see that they use Physlet image formation simulations in addition to a number of photos of actual demonstrations that we do in the live ILDs. And by the way, Rebecca, in the second half of this session, will give examples of how to use PhET simulations in a number of different ways, but we also use a number of PhET simulations in some of the other home-adapted ILDs. So let me summarize the steps, and you'll see they're similar to the in-class ILDs. Student downloads the prediction sheet. They read the written directions of the demonstration. They may view a photo, a sketch, or a video of the apparatus. They record their individual predictions and on a prediction sheet, and the instructor could ask that they email it to him or her after the session. Only after recording the predictions, they observe the demonstration and they describe the results on the prediction sheet and answer a bunch of probing questions that guide their critical thinking about the result. And again, this procedure is followed for all of the short demonstrations in the sequence. I'm not going to have you do this now because we are running out of time for our part of the session, but I suggest that after the session, if you want to try another one quickly, try the one called Newton's third law to play around with as another example, because it's a different one in that it uses technology. So additional notes. They incorporate prediction, observation, comparison. As I said, they use quality photos, videos, graphs, and simulations. And these materials that are in the home-adapted ILDs, you could use these in your class if you have no equipment to do actual in-class demos. You could actually use the videos and simulations and so on from the home-adapted ILDs in place of actual demonstrations. They're an active learning strategy that can easily be used by new teachers immediately. Now, they have not been research validated, and so we welcome anybody who wants to do a research study. We would welcome you to do that, and we'd be happy to guide you to do that. And they're free to use with your students. So that link takes you to them, and they are there all the time, and they're all 26 of them are free to use, to assign to students. So let me say that we are happy, Ron and I, to help you in any way we can with these or with anything that we talked about here. And we thank you for your attention. And we urge you to engage your students in the learning process. And we've given you examples of how to do that. And Rebecca is going to give examples in the second half of other ways to do that, especially using PhET simulations. So right now, I'm going to exit my PowerPoint. And if there are any questions, you can put them in the chat. And if we have any time left, Mike can share them. I think we're getting pretty close to the time that was allotted to our part. So, but it's up to Mike, of course. He's the moderator.
Yep. Thank you so much. There is, I think we have time for at least one question. Here we go. Could you speak about what typically does the instructor do with the prediction sheets?
Oh, okay. So you don't really do anything with the predictions because you might think you could do research with the predictions, but you can't do research with them because students sitting in a large classroom, if you're talking about the in-class ones, although I think it's probably true for the at-home ones as well, students, after they see the result, often will change their predictions because, you know, students don't like to turn in something that they know is wrong, even though we urge to them that a prediction can't be wrong because it's just based on what you know at that point. They might change them. So you can't use them for research. They really are not meant to be a guide to the instructor. They're meant to be a vehicle for the students to get their interest and to engage them in the process of learning.
And it makes it certain that they've actually been actively participating. So.
True.
Yep. Okay, well, thank you, David and Ron. If anyone has any additional questions regarding this first presentation, please feel free to continue to submit those through the Q&A or through the chat. But thank you so much for your presentation this first half of the event. We'd like to move on to our final presenter of the evening, which is Rebecca Vieira of PhET Interactive Solutions, or Simulations, I'm sorry. Rebecca?
All right, thank you. Let's see if we can get David to stop sharing his screen first. And while we're, okay, perfect. Okay, excellent. All right. Well, good evening, everyone. And I see we've got some folks from around the world. So happy day, wherever you are, whatever time it is. So just to give you a tiny bit of background on myself, I used to teach high school physics in the great state of Illinois and in public schools. But I've really benefited a lot from the things that were just shared. The interactive lecture demonstrations. I use them frequently in my classroom after I learned about them, and I think it was probably 2005, I think. PhET Interactive Simulations has also made a lot of use of this particular approach. So what I'd like to share with you now is some tools that you can use, because, you know, when we think about interactive lecture demonstrations, sometimes you think about equipment, although David and Ron have both shown you can use videos, you can use other different kinds of digital resources. And I also want to answer that question about what do you do with student predictions, because there's something at PhET that we've been trying to push students to do rather. So it's not so much about what the teacher does with the predictions, but then what the students do with it. So I'm going to be sharing a template for that. So I'm going to go ahead and pop up my screen here. And I am going to share my entire screen. Give me 1 second to do that. And I will get my slides up. And could I just get a quick confirmation from someone that you can actually see my slides? I'll need a verbal confirmation because I don't think I can.
We can see them.
Okay, all right. And it does look like, okay. And it does look like while I am sharing my slides, I'm not gonna be able to see the chat. So I will appreciate the help of what happens in the chat. So in like the 20 or so minutes that I'm going to spend with you, I'm hoping there's 3 things that can happen. If you've never accessed PhET simulations, I'm hoping to show you how to access them. But if you've used PhET before and you think that you're a know-it-all, which you may be, the reality is there's probably some simulations that are new that you haven't seen and different features. And I hope that you find at least one new thing that's helpful. The second thing, I'll share tools of interactive lecture demonstrations with PhET simulations, and then hopefully we'll have just a couple of minutes to think about prediction questions. But I do also want to share with you, like I said, some templates and ways to get additional information. But I'm going to put a tiny caveat and just say that the things that PhET has done with ILDs are some adaptations of things that you've seen. So I just want to save myself in case, you know, we show something that may not be 100% exactly, you know, compatible with what, you know, it's not that it's not compatible, but, you know, not exactly the same thing, exactly using the same methods as what you've seen presented. So I would like to start by just having people type one key on your keyboard. What's your level of familiarity with PhET? A 1 would be I've never heard of it, and 5 would be I'm a super user. So let me give people just a moment to do that. type them in. And yeah, if somebody could read out to me and just tell me, what are we seeing here? What kinds of numbers are we seeing?
I see a 4, 3, 4, 4, 1, 3. We're pretty much, I would say the average is going to be somewhere between 3 and 4 so far.
Perfect. Okay, thank you. All right. Okay, so that's great news. And if you're at a 1, that's totally fine as well. Just a little bit of background history. PhET Interactive Simulations is based at the University of Colorado in Boulder in the United States. It was started in 2002 by Nobel Prize winning physicist Carl Wyman. He basically wanted to he actually took the money that he won from the Nobel Prize for doing high level physics research. And he said what he wanted to do with his life at that time was to contribute to education. And that's actually what he's been doing for the past. So PhET simulations are these interactive things. They're kind of like virtual laboratories, but they're a little bit different. And our whole goal behind PhET is really to help students understand STEM by doing STEM. I'm really talking about math and science and fundamental concepts of STEM. So I'm not talking about the whole. Specifically today, you know, I know we're mostly physicists here, or, you know, physics related, physics affiliated. So I'm going to be speaking mostly about physics. We've got over 160 simulations, and these simulations, they're kind of colorful to look at. Sometimes they look a little like cartoons, but they were actually developed for introduction. They're all the way through university level. Education based. They take time to develop, but I think in the past year we released like 8 or 10 simulations, which means if you haven't been to the PhET website in the past year, you probably don't know what we have that's new. A couple of minutes to go to the website and to choose a simulation that maybe is brand new to you, or a simulation that you haven't seen in a while. And I want you to dig a little deeper. And I'd like to just, you know, think about, what do you notice? What do you wonder? So I'm going to click out of my presentation here, and I'm going to paste this link here into the chat. I'm so sorry about the recursive images. I'm going to go back to, I'm going to actually stop sharing for a second. No, I'm not going to stop sharing. I'm going to actually take you to the website. I know you can open up another window on your own, and you can also go into the website. So if you go to the website, there's a button right on the top, right on the front page. You can also go up to the menu here, click on All Sims or Explore Sims, and it will take you to a browser. And I know many of you are physics folks, if not all of you, so I would probably click on physics. And the newest ones will be near the top. So you'll see things like build a nucleus, Keplerly fabulous simulations. You might also see calculus grapher. It's a lot like Moving Man. We have this old simulation that where you drag a little man along. It's a lot like what David Sokolowski. Let me just pause real quick. I'm going to stop sharing and just see, did anybody find a new simulation? My voice is breaking up and it's hard to understand. Are other folks struggling with that too? Don't know if it's my speaker. Uh-oh. Uh-oh. Are folks still having troubles hearing me?
Rebecca, it sounds better to me now. It was breaking up a few moments ago, but it sounds
okay. All right. Okay, just let me know. All right, so it looks like
Okay.
some people are saying build a nucleus is new, collision is new. I also want to note somebody here says that sound waves, which they spotted a couple days ago, sound waves is actually a collaboration that ended up being kind of a crowdsourced simulation. It's a simpler simulation in some ways, but it might look a little different from our regular team simulations. Kepler's, ooh, the optics ones are new. Okay, good. I'm glad you're exploring those because I will hopefully have us come back to a couple of them in a moment. But I just want to say, as a teacher, it's very easy to kind of fall into that rut and say, I use this one simulation, I just Google that, you know, projectile motion and go straight to it. But check into our website, check into that main search page that are helpful to you. And I see Kazuo Cottrell, you're saying Energy Skate Park looks good. That's one of our most popular ones, along with the set that hopefully is helpful to you. I'm going to get into the ILD piece in just a moment here, but I did want to just say, you know, using simulations in the classroom, so they're open, that allow students to explore and ask their own questions, that really shifts classroom norms. I'm not sharing about FET's research today, but one thing we do know is that using FET simulation significant learning gains. And to use FET simulations is through interactive lecture demonstrations. We actually have an online course, highly detailed course, which is on Coursera, and we also have a general course on our website. Class strategies is one of the components, and within that we have four different things we focus on, but one of those is interactive lecture demonstrations. I'm just going to pop out of this for a second so that I can, oh, am I sharing my screen? Oh, I'm not sharing my, okay, sorry, let me go ahead. Let me share my screen real quick. There we go. Okay, here we go. So the thing that I wanted to share with you is this course that I mentioned that we have. I'm gonna pop it into the chat here. There we go. So you can visit that on your own time and take a look at what that is all about. But I'm just going to give you a little bit of a taste. So I also am curious to know how many of you have used interactive lecture demonstrations before. I'm not sure if I heard from folks. Is that something that's new? Using? I guess if I just ask the question, have you ever used interactive lecture demonstrations in your teaching? Just go ahead and type yes in the chat if you have, and no if you have not. And if I could get some help, someone telling me have you used them, or is this brand new? If somebody could read out to me what you're saying in the chat, that would be nice.
I've got 2 no's so far.
No's.
3 no's.
No,
Give me
okay.
a yes, somebody. Oh, we got a yes.
Oh, nice. Okay.
Oh, 2 yeses.
Okay.
3/4 no.
Great. All right. Good. I'm actually okay. All right. So it sounds like it's brand new for most people, and so I really encourage you to take up David's suggestion of getting access to that book. The book that he mentioned, you know, it gives you lots of these different templates for how to do, you know, templates for specific interactive lecture demonstrations, really understanding the process behind creating really good questions. And it is very possible to ask questions that are not very fruitful versus prediction questions that are extremely fruitful. And that's really what we want to go for. So I just want to show you, this is an example of an interactive lecture demonstration that I think could be fruitful, but is probably a little bit less so. But I'm going to use it as an example because it's simple and it will help you to see the way that PhET encourages people to make use of predictions. So build a nucleus, I heard, was new for many of you. So I'm going to go to that simulation. I will also pop it in the chat in case you want to explore it yourself. Okay, there it is in the chat. I'm going back into the simulation. So the question that we had on here is, we've got this xenon 109. It's a radioactive isotope that undergoes alpha decay. And we might ask the students to make a prediction about what that new isotope might look like after that decay, including the number of protons, number of neutrons, the mass, the charge, or the atomic number, and the isotope symbol. How would that new isotope look like this? What happens? So I recognize if students have no prior knowledge, this probably is going to have no meaning. With something like this, if they don't know what beta decay is, they have very little to go on. And it's probably not going to be a terribly productive prediction question. But if students have some familiarity, and perhaps you're using this as an evaluation of their understanding, I think it can be helpful. PhET simulation in this case, let me go back to the one that I have set up for us. This is really you can add neutrons and protons. You can see naturally whether or not it's stable. And I actually need to go up to, I think it said 109. I may be in a situation where this is a little hard to do. So figure out how I make myself oops, I got to increase there we go. There's our xenon. I'm going to go down to xenon 109. And then I am going to go ahead and prediction. I'm not just going to show them the answer, right? So let me go back into my slides. I'm just going to click through here. It's going to be easier for me. The way that PhET recommends that we break down this prediction sheet is we like to have really explicit moments where students do certain things. So we have them make a prediction. We also encourage students to write out their explanation. What do they think is happening? How is the mass going to change? How is the atomic number going to change, and why? We like students to really commit to that initial explanation. And we also like to have students at that moment, after they've written down their own explanation, to also talk with peers and to try to integrate a little bit of peer instruction into this. Then what we'd like to do is have students do the actual demonstration. I'm going to go ahead and have an alpha decay. It looks like we just lost a couple protons and a couple neutrons, and we've now gone down to, I don't even know what oh, there we go. Te is tellurium. So we have our answer, and within the context of this document, then students can write down what actually happened, what the actual outcome is, and they can provide an explanation if necessary. The thing that we like to do kind of beyond this is we like to have a section where students engage in some kind of analysis. This here is quite direct, and I would not always use this. Like, it's basically a paragraph, or where you give students a lot of structure in order to think about what's the process that I'm seeing here. Does the proton number or the atomic number increase or decrease? Does the mass number increase or decrease? Exactly what's happening. And then there's a bit of an application here. So this is just one example of one way that we think PhET simulations can be used with interactive lecture demonstrations. But there's actually lots of different ways to ask questions that can go much deeper and be quite a bit more complex and really go towards helping students understand what's going on. Some of you may be familiar with TIPPERS, which stands for Tasks Inspired by Physics Education Research. There's a great book out there called TIPPERS, Sense Making Tasks for Introductory Physics, and it shows actions you could ask students to analyze charts, changing representations, like what David and Rod showed with the, you've got position time graphs, but you can do velocity time graphs, acceleration time graphs, comparison tasks, all these different kinds of questions that you can ask. here's just a few that we think could be really good for interactive demonstrations. So if you build a circuit with the circuit construction FET simulation, and you have 1, 2, 3 light bulbs, and in that circuit, what would happen to the brightness of the first bulb if bulb number 2 burns out? This can be really tricky for students. And their answers to these questions, of course, will make it clear whether or not they deeply have an understanding of what's going on in terms of electric flow, resistance, etc. We could also have a question like, here's an electromagnet, and describe how that magnetic field strength changes at a point near the electromagnet at a fixed battery voltage. And again, explain your reasoning. We have a simulation all about natural selection. And here we ask, what kinds of conditions would you need to change in the environment so that the surviving offspring after multiple generations ends up being completely brown? So students would have to have some familiarity with the simulation. So perhaps that's something you show them in advance. They'd have to understand what they can modify in order for the elements of the system. You might also ask a question, again, that gets at reasoning, right? So what happens to the concentration of sodium and potassium ions? So again, it is a prediction question, but it's really going towards, the reasoning behind what's happening. So the thing I actually wanted to show you, I'm going to give you a link to this. We have a template that we recommend people use when they're using a FET simulation. So let me just make sure I get you the link here. And I will put it in the chat. There we go. And I'll just, this will be for you to take a look at your own time. But I did want to just highlight, some of the richness of what David and Ron talked about. The richness in that book is the questions and in those predictions. And what do we do with the student predictions? We really like, at FET to focus on the prediction with the explanation, which, I think is built into a lot of David and Ron's worksheets. And then we really like to, whenever possible, have students really, really nail down discrepancies. So what actually happened that might have been different from what I thought? And also, we really, really like to focus on what's that final explanation? How do students rectify their thinking or make their thinking more complete, more accurate if they found that their prediction was something that they hadn't expected? So this is just a little template that we use at FET, and it's been quite effective. This is what it looks like when it's kind of filled out. This was a ILD prediction sheet created by one of our FET fellows. I don't typically like to see more than one question on a single complex sheet like this. But what the teacher here did in order to prepare for an interactive lecture demonstration was to think about what multiple compelling answers that might come out. That means you've probably got a pretty good prediction question. I really like to look at common student learning challenges or misconceptions or naive ideas, and thinking about how might something discrepant help students to shift their thinking, and helping them to reflect on that. So again, this isn't something that necessarily as a teacher, as a teacher, I would love to see my students' reflection on how their thinking changed more than anything. I want to take just a pause here and share with you one more simulation about optics, because somebody mentioned that. And I'd like you to think about what kind of a question could you ask with this simulation. I'll actually give you the choice of Kepler's laws, which is brand new, or geometric optics. I'm going to put both of those into the chat. And I would like you to take a couple minutes and think about what kinds of questions, what kinds of prediction questions could you ask? And I'd love you to post them in the chat. And this will also give me a moment to check in with folks and see if I might have missed any questions. So here's geometric optics, which I'm putting in the chat. There's that. And I'm also going to pop in Kepler's laws. And again, the question for you is to choose one of those and think about what kinds of, predictions might you be able to ask students to make. And it's not always easy to come up with these questions. So if you're not fast about it, it's okay. They do need to be thoughtful. But it's good to start generating ideas. I'm gonna, as I give
Rebecca,
people just a couple minutes to do that.
There are a few questions for you in the Q&A, and I've taken some of the questions that were in the chat and pasted them into the Q&A. So.
Okay, got it. Okay, I'm gonna take a look. So
Okay.
One question here, I've started to worry about conceptual questions using light bulbs because students are no longer exposed to light bulbs with filament. I totally understand that, but I would say bring those filament-based light bulbs into the classroom. The point is really important, though, that you can't ask students questions about a scenario that they don't have some familiarity with. It's not fair, I think. That's part of the reason why I think it is important to have students have hands-on and personalized experience with equipment. Digital materials are not going to replace that, and I don't think they should. Could this be integrated with Nearpod to record student predictions? Yes, PhET actually is integrated already into Nearpod. They're one of our partners. So yes. John asks, are all physics simulations HTML5 now? And the answer is most of them. If you go into that filter that I showed you, into the page where you did see all the simulations, we've unchecked the Java and Flash simulations. So if you go in, you can find the old Java simulations, and many of them will run with a Java patch, but only on computers, I think. Does PhET still have a lot of Flash sims? I think there's only 2 or 3 Flash, and Flash truly and honestly doesn't work for anybody. And I think, unfortunately, the one that I'm really sad about is Lunar Lander. That one's in Flash and hasn't been converted. Yeah, I don't know about all the others, but they're still accessible on the website. You can get the files if you're able to run them. Okay, I know we have basically no time left. Does anybody have any interesting, we got some questions here. Okay, John Carzoli, what happens to the image as the object gets closer to the lens and passes the focal point? Let me go ahead and share my screen real quick just so we can see exactly what John is talking about here. Let me go into my geometric optics. Let me see. So I'm going to go back. I got to get back into my lens. And so I think the question here was, what happens to the image if we take the object? No. Take the object and go past the focal point, or the image and go past the focal point? Oh, yeah. Here we go. Take the object and go past the focal point. That's a great question. And I think it's especially a good question because our students are so good sometimes at drawing these static images of ray diagrams. But to really think procedurally about what's happening and what shifts at that moment of the focal point, that's a really good question. I like that a lot. I think I saw one more question. Kepler's laws. How can one ask about the speed of the planets? One can ask how the speed of the planets varies as it travels around the sun. I think is what we're talking about here. So here we've got this planet going around a massive object like the sun, and we can see how that velocity changes over time. So for a question like that, of course, we might need to be specific, giving them a particular scenario and asking them what would happen to it at various points or at this point. Let me see if there was one tiny last thing I wanted to share with you all. click through here. Yeah, I guess I just wanted to encourage people to learn more. I already shared with you the virtual workshop link. I'll post it in the chat one more time. You know how to access FET at this point. Everything's on the website, and everything from the website is free. So please consider using FET simulations for ILDs, because we love ILDs. They're super productive when they're well.
Did we lose Rebecca?
I think we did.
We did.
So, Mike, if you want to go ahead.
So Rebecca is unfortunately not going to hear this, but please let's give a round of virtual applause to Rebecca for her wonderful presentation. We can do that in the chat, and she will see it later. Thank you so much to David and Ron. And I believe, David, you want to talk about your short course for just a moment here?
Thank you, Mike. Yes. So I don't know if you can see this slide or not. It's down in the slides at the bottom, and I see it on my screen. Can they see it, Mike?
Yes, they should be able to see it.
Anybody? They can see it? Okay. So we're holding a short course, 2.5-day course in July in Portland, and we welcome any of you to come, and you can find a link in the resources that will take you right to the web page, and you can find out all the information about it. So please consider this. Thank you, Mike.
Rebecca's
Absolutely.
back.
Rebecca, you're back. Any last words?
I'm so sorry. I clicked in the wrong spot. But anyway,
It's okay.
I'm done. So it happened at the perfect time. I am around. I'll drop my email in the chat in case anybody wants to get in touch with me. And if anybody wants to be part of a more extended course through FET, we have an opportunity. Drop me an email and I can get you in. That's it from me.
Poland just asked in the Q&A, can you please share the link again? I'm not exactly sure which link, because I know you shared a number of links. So
I just popped the FET virtual workshop in there. I will pop the FET main webpage. One of the
David,
two.
can you post the link to the active learning short course in case that's what Poland was looking for?
Yeah, I will do that.
Okay, so you could, okay. Well, thank you so much, everyone. At this time, we're gonna wrap things up. We want to be respectful of people's time. I just also want to say, be sure to register for next month's episode of Video AAPT, which will take place on February 22nd at 7 p.m. Eastern. The topic is engaging students with realistic virtual physics labs. It's sponsored by Polyhedron Physics, and the presenters will be Eugenia Itkina and Al Bachner. So for more details on that, you can visit aapt.org/video, and we hope to see you there. In the meantime, thank you to our presenters again, and thank you all for attending, and have a great evening.
Thank you.
Thanks.